Dear students, in this lecture we will discuss about Diels-Alder reaction. Diels-Alder reaction is the example of cyclodation reaction. And is concerted single step reaction. For example, we take 1,3-butadiene and ethylene and they react together to form cyclohexene. This reaction is 4+2 cycloaddition because 4 pi electrons from diene take part in this reaction and 2 pi electrons from alkene, which is ethylene, and this is also called dienophile, and this is diene. In this reaction, cyclic transition state is formed because the arrowheads and tails represent the formation or breaking of bonds. So all the bonds are represented as dotted bonds in a cyclic manner. For example, a new bond is being formed between these two carbons, so it is represented as dotted bond, and a bond between these two carbons is being broken, which is shown by the arrow tail here. So this is also represented as dotted bond, and so all the rest of the bonds. So, and same is the case for all the bonds. So thus we get this cyclic transition state. In general, because there is excess of pi electrons on diene, so it can be regarded as nucleophilic, and dienophile as electrophilic. Although it is true that both of the molecules are taking electrons and donating electrons at the same time, but excess is present on diene, that's why we can regard it as nucleophilic in nature, and in general electron donating groups are present on diene, which can be alkyl groups, and similarly electron withdrawing groups are generally present on dienophile, and they can be nitro, halogens, keto group, esters, etc. Now if we see that in general this diene can exist in two forms. This form is as cis and this form is as trans. Why we call it as cis or as trans? Because of the sigma bond or single bond here, and due to free rotation both of these forms are interconvertible. However, this is only cis form which can take part in Diels-Alder reaction. As trans form would not take part. However, it is first converted into as cis form due to free rotation around the sigma bond, and then it takes part in Diels-Alder reaction. However, in cases when S trans form is fixed, for example, we have a cyclic molecule and now free rotation has been restricted here, so this form cannot take part in Diels-Alder reaction, so it would not take part. This isomerism is comparable to general alkenes, which can also be trans or cis. However, these two forms are not interconvertible because we have a double bond here and free rotation has been restricted. So these are two different compounds. So this is some basic information about Diels-Alder reaction, and now we see some examples. Okay, now we discuss the stereochemistry of the products of Diels-Alder reaction. For example, we have this diene and it is allowed to react with this aldehyde. So Diels-Alder reaction 4+2 would take place and we would get this molecule, and here we can see this molecule is chiral in nature. Therefore we will show the isomers, enantiomers. This is the enantiomer with the aldehyde group above the plane, and second would be the other one, the other enantiomer with aldehyde group below the plane. And for example, we have this molecule, again cyclodation reaction 4+2 would take place under similar conditions. In this case, cyclohexadiene would form because here was a triple bond, so one bond would take part and other two bonds would remain as such. And here we do not have chiral centers because both are unsaturated systems, sp2 carbons, and chiral centers are on asymmetric sp3 carbons. So these are two examples. Okay, now we see another example. In this case we have this is cis alkene, so both of the groups are on the same side. In general, Diels-Alder reaction takes place via retention of configuration, so both of the groups will retain the configuration, and if one of the group is on the above side, other group would also come on the above side of the plane. Because we have discussed that it takes place through retention of configuration. So in originally the starting material we had both the groups on the same side, so in the product as well they would appear on the same side. And in this case we can see that there is a plane of symmetry. So this molecule would be meso. So we do not have to draw the other molecule, other isomer, stereoisomer, this one. So we would just cross it because this is meso. If we take another example in which both of the groups are trans to each other, so as a result we have similar conditions. We will get one group on the above side, and now because both are in the opposite direction and on the opposite side, so if one is above the plane, so other one would come below the plane. As we have discussed that Diels-Alder reaction takes place via retention of configuration and is stereospecific in nature. So I hope this is clear to you. Now we see some more examples. In our previous examples, we discussed the stereochemistry of the substituents on dienophile, and now we discuss the stereochemistry of the substituents on diene. For example, we have this molecule, and we react together these two molecules under Diels-Alder reaction conditions. Because this carbon is not chiral or not asymmetric, because all the four groups are not different. These two groups are same, therefore it cannot be regarded as chiral center. However, we have chiral center here, so if we put it above the plane, this would also come above the plane. If we see it, why? Because Dyneins can have two types of substituents: outside, inside, inside, outside. So these two substituents on the outside, therefore if one is drawn above the plane, so other would also be drawn above the plane, and in this case we can see plane of symmetry is present again. So this is mesomolecule. Now we see another example. In this case again, we will get cyclohexene ring. And now one of the methyl groups is inside, so if this is above the plane, other would come below the plane. And the other isomer, in other isomer it would be below the plane and it would be above the plane. One more example related to this topic. In this case again, first we would draw cyclohexene, and here again no chiral center, so we do not need to show chiral center. And if it is drawn above the plane, it would be drawn below the plane, and the other one below the plane, above the plane. And why these two substituents have different or opposite stereochemistry? Because we know that the Diels-Alder reaction takes place via retention of configuration, and one of the group is on the outside of diene and other group is towards the inside of diene, so they both have opposite configurations, and this would be translated into the products as well. So it would be above the plane, it would be below the plane, and if it is below the plane, the other one would be above the plane. Now we will see the examples in which both the diene and dienophile have substituents. For example, we have this diene and it has substituents like this, and we have dienophile, for example, it has substituent like this. In general, a dienophile can attack a diene via two approaches. For example, one possibility is that it can attack or react with diene with the substituents in the away position, or it can react with diene when the substituents are towards the diene. So this approach, when the substituents are away, this is exo approach. And if the substituents are towards the diene, this approach is called endo approach. So we can draw this here as well. This is exo, exo, endo, endo. So in general, we have two types of substituents on diene, outside and inside, and there are two types of possibilities via those the dienophile can react with diene. This is endo approach or exo approach. Exo approach is that in which substituents are away from the diene, and endo approach is that in which substituents are pointing towards the diene. And if we see that the inside substituents are far from the backbone of diene, just like in exo approach they are far from the backbone of diene. So inside and exo substituents would have same stereochemistry. So inside would have almost same stereochemistry like exo, and endo are coming towards the backbone of diene, and outside substituents are also nearest to backbone of diene. So these two have same stereochemistry. Now we solve this problem using these models. If we have exo approach here, we will get the cyclohexene first. Now if we put this substituent on the above side, the other substituent would also come above. And now this is inside, and this is exo approach. Inside and exo have same stereochemistry. Inside and exo have same stereochemistry. So this would also come on the above side of the plane. And here we can see there is plane of symmetry. So again this is meso, and we do not need to draw, or we can draw it and we can cross it because this is meso molecule. Now if same compound reacts via endo approach, if the examiner gives you the reaction of these two molecules and does not show exo or endo, it means you have to write both of the options. However, if he mentions the product should be exo or endo, then you have to mention only that particular product. In this case we are using endo approach, and we can draw the product. Now if we put this on above the plane, this would also come above the plane because these both of the substituents have same stereochemistry. However, in this case this one and this one have opposite, because inside and exo had the same and inside and endo had different. So this is, if this is above the plane, this would come now below the plane. So we will get this endo product, and again we have a plane of symmetry here, so this is meso. I hope the stereochemistry of the substituents on both of the diene and dienophile is now clear to you. To make it clear further, we take another example. Here I would like to ask you to stop the video and try it by yourself, and we can do it here as well. If this is put on the above plane, this would come below the plane because they have opposite stereochemistry. And now here they have again opposite, and this one is having same configuration because we have already discussed that inside would have same stereochemistry as that of exo, so this would also come above the plane. And this is endo substituent, and endo and outside have same. Endo and outside they have the same, so this would come on hashed wedge. So this is our product. Now we see the examples of cyclic dienes. Now if these two reactants are reacted together, this would attack here, this would attack here, this would come here. And in cyclic diene we can make 6-membered ring like this, and this is the bridge, this one, and this is double bond which is coming here, and this is coming from this bond is coming from the dienophile. Now this approach is exo approach. So inside this bridge is towards the inside of the molecule or diene, and it has same stereochemistry just like this exo substituent, so it would also come above. This is exo product, and if we draw endo product, this would come down. So with endo approach, the substituent would be towards the backbone of diene, and of course this is opposite to inside substituent, and as a result, if this is on the above side, the substituent would come on the below side. So I hope this is clear to you, and if you find any question or confusion, please leave your questions in comment box. Thanks.